All right. Okay, for use. Well, today you actually get a lesson streamed same day from me. So look at that. Mostly because I couldn't find an older version of it. But here we go. And today we're going to talk. Yes, it is. So today we're going to look at the Bohr model of the atom. And the question is this. If our model of the atom is this, which is protons and protons and neutrons surrounded by electrons in an orbital that are spinning around, why don't the electrons eventually spiral their way into the nucleus? Why doesn't their orbit decay? We know that protons attract electrons. We know they're in an orbit, but even in our solar system, for example, orbits are all spreading out or moving into the sun. Slowly but surely. And at the speed at which electrons move, why don't they collapse? Why don't they crash into the nucleus? And the basic math, if you treat these like particles, if you treat them like particles, just like any other that are rotating around a body, the math tells us that's actually what they should do, but they don't. They're found in fixed orbits. So, in the planetary model of the atom, in this model of the atom, the electron should emit energy and spiral into the nucleus. And this is important to understand, which is that it takes more energy to have a wide orbit than it does to have a close orbit. And of course, the least amount of energy would be to not be orbiting, but just be stuck to the nucleus. So you have to think about tracking energy. And the basic idea is that as the orbit decays, it should release energy. This is what happens with us, by the way. If you go into orbit Earth, as you move in, energy gets released. In our case, it's the form of like heat falling off a planet. But this is where a scientist named Niels Bohr to study this. So a scientist named Niels Bohr used the emission of light by hydrogen under voltage to explain this. And I'm actually going to demonstrate this for you later on in the class. I'll pull you guys aside. And if you're away today, I'll pull you aside and show you at some other time, but we'll actually put some hydrogen gas under some voltage. But in order to explain electron orbitals. And he discovered what we call quantum theory. And basically what we call quantized energy states solve our orbital problem. So what does it mean for something to be quantized? Well, we'll take a look at that. By the way, of course, you can pause this video at any time to get time. I'm going to move fairly quickly through it. A, because I have 17 minutes to get this done, but B, because better to have you be able to pause a video than to have the video go on forever. So basically, this is Niels Bohr, and what he found is this. When hydrogen is energized, it emits light, but it emits light of very specific wavelengths. And remember that when we're talking about light, when we're talking about electromagnetic radiation, this is the energy of that light. We see different wavelengths as different colors. But what is actually happening is that it is emitting electromagnetic radiation of specific energy levels, and we see that as color. And so the light is made by electrons changing orbits. So if we look at hydrogen, hydrogen has a proton in the middle, and then it's got an orbital. That's the worst orbital anyone's ever drawn in the history of humanity. Okay, we'll do that. It's got a proton in the middle, and that's got a lonely little electron here, right? Lonely little negative charge orbiting in that first orbital. And what can happen is that ray of light, oh, that's not what I want at all. That ray of light can strike it, all right? So we can have light energy. Or, sorry, not light energy in this case. Sorry about that. We're talking about putting a voltage through it. So we can apply electrical energy. In other words, like just plug it into the wall, give it a voltage. And like you're going to see, this glows. But what's actually happening is this. That electron is all of a sudden being given a bunch of energy because we've just shot it through. And so what's going to happen is the electron is going to jump up to a higher orbital. All right? So it's going to move to a higher orbital. And a higher orbital means it has more energy. So the electron moves to a higher orbital. And it does that using the energy it absorbed. But it won't stay in that orbital. There is an attraction from the nucleus, and this orbital underneath is empty. And so what's going to happen is that it's going to fall back down, or it's going to go back to what we call its ground state. It will go back to the orbital that it normally wants to go to, that it normally resides in. And so we'll have these two orbitals again, and that electron is going to make its way back down to the first orbital. Falls back down. And obviously we still have a proton in the middle. So the electron returns to the ground state, which is to say its normal orbital. But all that energy it had absorbed has to go somewhere. Energy can't be created, it can't be destroyed. And so what happens is that energy gets released, but it gets released in the form of light. It gets released in the form of electromagnetic radiation. So energy gets absorbed, and then it gets released. I don't know why I put released in brackets. I wanted to put the word light in brackets. And if you find that you've drawn this a little bit too big on your page, what I would do is just highlight it with your pen, just like this. Just shrink that bad boy down a bit. Oh, look, now it fits. Beautiful. So the electrons return to the ground state. The energy they absorbed now gets released. And that's fine. But what is noteworthy is that, like we said, the light only comes in certain frequencies, and that's going to be important. So what we can say is that the energy of the light is the difference in energy between being in those two orbitals. So basically, it takes more energy for an electron to be far away from the nucleus out here than it does to be close to the nucleus there, right? Makes sense. It takes more energy to keep something spinning away. And so when it goes up to the higher thing, it had to get energy to do that. And when it goes back down, that energy has to go somewhere, and it happens that that gets released as a wave of light, a wave of electromagnetic radiation. So why does that matter? Well, if we go to the next page, we'll see that this is what happens when hydrogen gets given a voltage, is that we only have 1, 2, 3, 4 distinct lines. 4 distinct wavelengths of light. And Niels Bohr is able to interpret from this something very important, which is that this is not what it would look like if an electron just spiraled down. If an electron spiraled down, so if its ground orbit was here, and it had been way out here, and it spiraled its way down to its ground orbit, you would see that here it's losing just a little bit of energy, and a bit more and a bit more. And what you'd expect to see is a whole rainbow of light. You'd see all kinds of different wavelengths of light as its energy level changed slowly from one thing to another. You would see a whole bunch of different emissions. But you don't. Instead, what you see is these perfect emissions that are always very consistent. And the fact that those perfect emissions are very consistent means that there's 4 exact changes in orbit that happen with hydrogen's electrons. And if you look here, what those changes are is from orbital 3, which we say n equals 3 down to n equals 2. That's a release of light. There's n equals 3 going down to n equals 1. There's n equals 2 going down to n equals 1. And we can even get up into the 4th orbital and things like that. But there are specific orbital changes that give specific energy levels. But they would only give 5 fine, perfect lines like this, right? Like we see here, if the orbitals are always in the exact same spot. And so the thing you have to understand is that this only makes sense if only very specific changes in energy level are possible. All right, hello. So Bohr shows that since only specific wavelengths are possible, only certain orbital distances are possible. You can be in the first orbital, you can be in the second orbital, but you can't occupy the space between them. Only certain orbital distances are possible. Because again, if it was possible to be halfway between the two, that would give you another line in here. And if it was possible to be 2/3 of the way through it, you'd get another one there, and 1/3 of the way through it there. And what about a quarter, right? And so on and so forth. And eventually you'd fill that whole rainbow in. But we don't see that. We see only specific lines, which means it's possible to be at certain orbital distances, and any other distance is impossible. And distance is a little bit of a quotation marks. We'll talk more about what that means in future lessons. But for now, distance works. But the second thing that is weird to think about is electrons must move between orbitals instantly with no path between, which just follows from the first. If you can only be in orbit 1 or in orbit 2, and you can't be between them, then if you transition from orbit 1 up to orbit 2, it can't be by slowly moving between them. It can't be by spiraling the orbit wider, which is how we would do that with like a rocket ship or something. It must just be an instantaneous move. You stop existing here and you start existing there. Now that feels completely wrong when you think about things on the level we live at. I can't stop existing at my desk and start existing at the door without traveling between the two. I have to travel the distance. But Bohr's model of the atom says that that thing that is obviously true for us on a big scale isn't true for the electrons in an atom. In fact, the maths tells us precisely the opposite, that they live in what we call quantized states. So this is called quantization, which is that only certain energy levels are possible and nothing between them is possible. So this is called quantization. And quantization is quantity, right? It's basically saying that certain quantities are allowed and other quantities are disallowed. So this is quantization. Certain energy levels of an electron are possible. And all others are impossible. Even for short periods of time. So instead of saying, we'll just say nothing in between them. Now this may sound like a really bizarre observation that doesn't seem to make sense, but B, it may sound sort of like a little observation, sort of a trivial thing to discover, but actually it ends up being the most fundamental discovery about how atoms work. First of all, it explains why atoms don't collapse. It explains why orbitals don't decay, because you can't get less energy than that first orbital. There's no path to get down into the nucleus outside of major external pressure, neutron star or some such thing. But secondly, it opens up the doorway to understanding how electrons and protons and neutrons actually interact. This is what's going to lead us to understanding why the first orbital can hold 2 electrons, the second one can hold 8, the third one 8, the fourth one 18, and so on and so forth. It is this quantization that in grade 11 chemistry, I told you, just don't worry about it. Just wave your hands, just trust me. Even way back in grade 9, we said 2, then 8, then 8, and just shut up. Just that's how it works. But now you're going to see that there's a mathematical basis for that. So, morning. So today we're going to learn just the most basic of that, which is that this tells us what Bohr discovered is what we call the principal quantum number. And up till now, we've always just called that the shell number. So until now, we've called this the orbital or shell number. Yeah, so basically, the easiest thing to do might be just to draw, I don't know, a sodium ion. Or a sodium atom, rather. Okay, so in sodium, we have 11 protons, and is it 12? It is. 12 neutrons in the nucleus, just like that. Whoa. And then, from there, we can have 1, 2, 3 orbitals. Shh, guys, I'm recording a lesson. Shh, thank you. And of course, we know that there's electrons in the first orbital, and we've always taught you that 2 fit in the first orbital, so we'll just draw those. And we've always taught that 8 fit in the second orbital, so we'll just draw those. And we've always learned that 8 electrons can fit in the third, but this is sodium, which only has 1 electron in its outer orbital, so we'll draw that. And basically, the principal quantum number is such that for this electron, we can say that for this electron, n equals 3, i.e. it's in the third orbital. Whereas for these two, and all the other ones in this orbital, we could say that n equals, that's right, Tiana Moody, n equals 2, because it's in the second shell, right? And the other thing we can say is that this is higher energy than that. This would have higher energy. And then, of course, the lowest of them all, in this case, is this electron here and that electron there, both of which have a principal quantum number of 1, which tells us that they're in the first shell, and that, of course, has the lowest energy level of these. The lowest energy level possible is the first shell. So quickly, all of these electrons are also described by saying they have an n value of 2. Excuse me. So the principal quantum number n tells us which orbital an electron can be found in. So principal quantum number n tells us which orbital an electron is found in. So I'm going to give you some homework. Not major homework, some minor homework, but here's our homework. I want you to draw 3 Bohr-Rutherford diagrams, just like we did above. And if you need help drawing Bohr-Rutherford diagrams, you can look in your grade 9 notes, grade 10 notes, grade 11 notes, YouTube. You can come ask me. But draw 3 Bohr-Rutherford diagrams for any 3 elements. I don't care which you pick. And identify, and I need you to identify the principal quantum number for each electron. And you can do it the way I did up above, where you can just circle them. You could use highlighters. Highlighters are great. Big fan of highlighters. Everyone likes a highlighter, right? So we can say that that one has n equals 3. These ones have a value of n equals 2. And these ones here have a principal quantum number of 1. All right, but we just want to make sure we're comfortable with that, because after this lesson, we're going to get talking about quantum theory in a bit more detail and with a little bit more sophistication. So we got to make sure we're comfortable with this so that we can move on to that. All right, well, thank you very much. Yeah, come talk to me if you're confused.